Hi everyone, I'm Ed Saunders. I've been training machine learning models since the early days of Kaggle, well over a decade now. Today we're solving LunarLander from scratch with policy gradients. We build the Python code step by step using pure intuition, train a neural network to pilot the lander, and record its landing videos. By the end, you'll understand the algorithm, the math, and the code. So let's get into it. We have imports for PyTorch here, and we have a few warnings so that we can focus on the code and not the annoying error messages or warnings. And we have matplotlib to plot some graphs which are going to be useful. And we're using Gymnasium. So let's just run this. That's just import. And this is where the magic happens. This is pretty much a standard boilerplate code, copy pasted from Gymnasium. So if you have a look here, it's basically setting up Gymnasium, the environment, and have a loop where stepping the environment and adding up the rewards and see what happens at the end of the episode. We got something very similar here. We have the max episode steps. The action is hard-coded at the moment, and this is where we're stepping the environment. And once it's done, we just get out of this loop, and that's pretty much it. The only significant difference we have is we're recording the video into the video folder for every 100th run, so that we can just replay the video as many times as we want. So let's just run one, and then have a look at the video. So this is where the video is. We're doing nothing. Action 0 is doing nothing. See what happens. We're crashing. It doesn't look good. So let's have a look what actions we have. With LunarLander, we have 4 actions, and we have the observation, which we call state, is an a-dimensional vector. So let's just have a look at the 4 actions. The first action is doing nothing. That's what we're doing. That's 0. 1 is firing the left orientation engine, main engine. Third one is the right engine. So let's just fire the left engine and see what happens. Rerun and play the video. So we're doing a flip, which is even worse. Let's just fire the main engine and see what happens. Are we flying away? That's none of them look really good. Okay, now let's have a look at the reward. So what we need to do is we're going to get a reward after each step, and let's just collect them, and we're going to plot the rewards here. So let's just create an empty array, and once you get the reward here, we just add it to the rewards array. So just append it, and then run this, and then we can plot the rewards. So it doesn't look too good. We got negative rewards all the way through, and at the very end we get a -100, and see how this happens. So rewards is basically we get a -100 for crashing, or +100 for landing safely. We got 10 points for each leg that is contact with the ground. It doesn't happen here because we're flipping. But let's just do nothing, and then hopefully at least one of the legs is going to touch the ground. And yes, it did. So we got a +10 here. Let's have a look what it looks like. Yeah, so we did touch the ground, but then we get a -100 immediately. So we have to come up with a better plan than just doing nothing. And the way we're going to do this is let's just understand what feedback we have from the environment. So we got a state, a reward, a terminated/truncated, which basically an indicator whether the whole episode ended. We can feed this back to the model, but the state would be a better option. So let's just have a look what the state looks like. Show the state. We can see it's a vector, and these are coordinates, velocities, angular velocity, and the 2 booleans that represent whether each leg is in contact with the ground or not. Let's just have a look at shape. It should be a vector of 8. It is. So this is what we're going to feed into the neural network. And what we're going to get from the neural network is probabilities, which action to choose. It's going to be a gradient-based model. It's not going to be deterministic which action we're going to choose, which is going to get the probabilities of from the policy, and we're going to choose based on that. Let's just create a multi-layer perceptron with an input of 8 and the output of 4, which is pretty much a fancy name for a neural network with one hidden layer. So we're going to call it policy. So policy is going to be sequential, and we're going to have a linear layer with 8 inputs and 128 hidden features. We're going to have a ReLU activation, which is pretty much keep only positive numbers, and another linear layer with 128 inputs and 4 outputs. So this is all right. And let's just implement it the simplest way possible. So let's just feed the state into the policy. Let's see what happens. We get an error because it must be tensor and not a NumPy array. So what we do is convert this to a tensor. And now we got the outputs, which is fine. These are obviously not probabilities because they are not between, they don't add up to 1, and they're not between 0 and 1. These are called Logits. But we can easily convert this to probabilities using softmax. So probs is going to be softmax to the Logits, and see the probs. So this works. These add up to 1. And it's a kind of uniform distribution, not quite, because then everything would be 0.25, but not too far. And the issue is that we have to set the dimension, and we only got one dimension, so let's just use the last dimension. It's going to be fine. So these are our probabilities. This is good. So now we have to sample based on these probabilities. So the first action, which is doing nothing, that's going to be selected by the highest probability. Action is going to be multinomial probs and one sample. Let's see, the action is a tensor. So it's the second one, which is firing the main engine. But we have to convert this into a number to be able to use this as the index. So this is the action item. Basically, this is the selected action, this one. Let's just feed this back here. Instead of action equals 0, we're going to have action. It's going to be this one. Let's have a look. All right, so given this is almost a close to uniform distribution, the results are going to be quite random, or at least they're supposed to be random. Let's just try it again and see what happens. Okay, so here it's actually quite random. It's fine. And we have a look at the rewards. It looking a bit better. So we have some positive rewards, which is pretty good. And we got a +10 for touching with one leg, but then we're still crashing. But the good news is, based on the rewards, we can start training our model. With the rewards, it's fine, but it's only a feedback of the current state. We're not looking into the future, and we really should, because if you're doing something wrong here, it's going to have an effect right here. So if you start flipping, for example, we're going to crash eventually. So we really should look into the future. And also, if you're just landing really smoothly in the middle, it's still going to have a huge effect on what's going to happen in the end. What we need to do here is come up with a return which actually does look into the future. And the way we do this is, for each state, the return is going to be adding up all the rewards in the future, but discounting them. Because if we don't discount them, it's mathematically it's not going to be stable, and we don't want to look into the future forever. Because let's assume that we can stay in the air forever. Our model may just come up with a solution that it's going to be hover for forever, because then the reward is going to be infinite instead of the +100 for the landing. So what we need to do for each step, we have to assign a return. We're going to go backwards from here, And for each state, we're gonna assign the reward in that state plus the discounted returns in the future. So let's just call this returns. It's gonna be an empty array. We do a whole rollout, which is this. So basically playing a whole episode, we're gonna end up with the rewards, and maybe we can actually create the returns here just to see that we're not using it beforehand. So return is going to be an empty array, and let's just iterate through, but we have to reverse it. Okay, so we're iterating through the rewards, call it reward, and we're gonna use another variable called g, which is gonna be the running return. So basically it's gonna be the return. So g is gonna be g discounted, the previous g discounted by 99%. This is 99% is quite standard because it looks into the future quite a bit. Roughly 200 steps into the future, we're still considering the return in 200 steps with around a 10% discount rate. But if you look into the future, like 1,000 steps, it's completely diminishing. This 0.99 on the power of 200. It's going to be 0.13. So 200 steps in the future, we're still considering that with a 13% discount, whereas 1,000 steps in the future, it's 0.0004. It's very little number. It's insignificant. So 0.99 works really well as a standard discount rate for reinforcement learning. This obviously, given we start from 0 in the first step, this is going to be just 0 plus the reward in this step, and that's it. Returns, we're going to append g, which is perfect, but now given we reverse the rewards, the returns is also going to be reversed, so we have to reverse it again. You reverse it back. So returns.reverse, it's going to reverse it back at the end. If you run this and plot the returns as well, again, to have an intuition, at the very end, they are the same. So the orange is the returns, and these are the rewards. And basically, we're doing quite bad all the way through. What we can see, we're doing even worse. It's pretty much straight before landing, but we're doing actually quite well here because we get a plus 10. We want to maximize this. We want to make sure that this is mathematically stable. To do this, we have to normalize this. And the easiest way to normalize it is divide it by the mean. That way, roughly half of this is going to be above 0, other half is going to be under 0, and also divided by the standard deviation so that we end up with a standard deviation of 1. This is a good time to convert our NumPy, a Python array of our NumPy numbers, to Torch. So just to show you, so returns is just a normal array of NumPy numbers. So the way we do this, given these don't have gradients, we can just do this, torch the tensor returns, and that's it. And now let's normalize it. So returns, it's going to be equals returns minus returns.mean divided by returns.std plus a tiny little number called epsilon, just in case the standard deviation is exactly 0, and then the whole thing just wouldn't work. So we want to have a tiny little number here just for numerical stability. Have a look at the returns and run again. Okay, this is pretty good. So we want to push this up. That's what we don't want to do. We want to maximize the returns. We want to be confidently right. And to do this, we have to multiply the returns with the probabilities of the action we chose, just to make sure that we confidently right, not just right randomly. We got the actions here. We want to have the probability of this action for each steps. So action probs, it's going to be probs action. That's all. Let's just plot the action probs as well. we have to run this first, and then this one. And this one doesn't work because this one has grads attached to it. So let's just have a look what's inside this. So the action probs, we have grads here because the way we ended up with these probs is from the neural network. So they have gradients attached to them. That's what we're going to back propagate on when we're going to train the model. Unfortunately, Matplotlib is not really good with displaying tensors with gradients. So what we need to do, we need to detach it. What we could do, just iterate through this and convert to an item. That's really an option. So x.item for x in action probs. So this should work. What we have here is 0.25 roughly for each action, because at the beginning we end up with roughly uniform distribution of actions. So what we're going to do is we're going to multiply the returns with the corresponding probabilities and maximize it. So this works well, but the issue we have here is the probabilities are going to be between 0 to 1, which is a quite small range. We want to have a much bigger range so that the training is more stable and we don't have vanishing gradients. So what we do is calculate the log of the probability. So basically 0 gets converted to minus infinite and 1 gets converted to 0. Basically 0 to 1 range gets converted into a minus infinite to 0 range. So the way we do this, let's just rename, it's going to be action log probs. Just apply the log, that's all we need to do. And do the same here. Okay, this is better. So the log 0.25 is around this. So what we need to do is maximize so we get the returns, we get the action log probs. What we need to do is just do an element-wise multiplication and maximize it. The objective is going to be, action log probs times returns, and this is good, dot sum. But how do we maximize? It's a bit tricky because all the neural network training optimizers want to actually minimize. So we have to have a loss function, and the loss function is just going to be minus objective. So if we're minimizing this, then we're maximizing this. This is going to work quite well. That's pretty good. Now all we need to do is put this in loop. So episodes, let's just say 2000. And this is where we're going to have our loop. And so let's use RMSprop optimizer, quite similar to the standard stochastic gradient descent, but this one tracks the momentum of the gradients on a per weight level and adjusts the scale of the learning rate. This works really well for reinforcement learning. So what we need to do, just provide this with the policy parameters and the learning rate, which has a learning rate 0.01. Let's just use that and see whether it works. Okay, so all we need to do here is zero out the optimizer. So optimizer is going to zero the grads across the policy and the softmax and everything that we do all the way up to the loss. Then we're going to do a back propagate, and what we're going to do next is step. What it does, it's going to multiply the negative learning rate with the gradient plus apply the scale of the RMSprop. So if you run this should work, but let's have a bit of feedback. So let's say that if for every 100 episodes, let's print some stuff. This is going to be a range. We're going to end up with one extra episode, but then we're going to have a feedback for the very last episode as well, for the 2001st. Rewards and running steps. So how many steps we managed to take. The more steps we take, we probably flying a tiny bit better. We got an issue here. The action log-probs is a Python array of tensors. That's not good. It should be a tensor. Action log-probs is it gonna be, yeah, torch.stack. Okay, let's see what happens. So this one doesn't work. np.mean rewards. So the running rewards, it's gonna be, yes, that works. Take the mean of the last 100. Okay, let's run it and see what happens. So this is good, almost, but that's not the mean rewards. We need the sum rewards. Let's do it again. Yeah, it's looking better. The reward is getting worse. That's probably the huge learning rate. Could be something else. It's getting actually better. It's getting much better. The learning rate of 0.01 from experience is huge. So let's just start with a smaller learning rate. Better learning rate. But let's just do it again. Start from scratch. It looks more stable. So reward is increasing steadily. Steps are also increasing steadily, and it takes longer because now the rollouts take longer. So it's actually getting better. So let's have a look. So this is looking actually pretty good. It's getting much better. So we're at step 1400 and it's getting really good. It's not quite landing where you want it to be, but it's still landing, which is good. After step 1500, this is where we're at. It's going to get better. It's steadily improving, but I think it's a good time to reflect. So we officially built LunarLander. It works, it lands. There are obviously improvement opportunities, but it's a working reinforcement learning algorithm, actually called the reinforce with capital letters. So we're at step 1900, almost finished, and we see it's the results kind of stabilizing. We're not really getting over 100 reward, but it's landing quite nicely. It's not the best possible, but it's certainly really good. And this is a proof that even a simple intuition-based reinforcement learning algorithm can work. So this algorithm is actually called the reinforce algorithm with all capital letters, and there are obviously improvement opportunities, but this video's goal was to have an intro into building a reinforcement learning algorithm from scratch and based on pure intuition. And there we have it. See you next time.